Hello and welcome to the JE Plugins channel. So it's been a while since I've done an upload and I've had a lot of time to reflect on what I want to do with this channel. So the first change we're going to make is I'm actually going to be talking on the microphone for a change rather than the AI voiceover. And also I'm going to see about switching things up. So I'm going to carry on with this audio DSP series, but in the future I'm thinking about expanding into general digital audio education. So if there's any suggestions for videos, please list them down below. Anything to do with audio, nothing is off topic, but I will continue this DSP series. So this is episode 4, and today I'm going to be talking about delay effects, or the basics of delay. So delay is very common in audio plugins and audio processing in general. It's a required element in a lot of audio effects. You require delay for, delay plugins for one, artificial reverb simulations, chorus effects, modulation effects, and plenty more. And so we do this by shifting the phase of a signal and playing back the resultant waveform with combinations of the original waveform, the new waveform, and various amounts of feedback. So the most basic form of delay is on a sinusoid. So if you have like a tone generator with the traditional sine wave formula, there's a variable that allows you to shift the phase of that sine wave, and that is essentially just adding an offset inside the sine term. And when we do this, applying a shift of 2 pi essentially creates an identical signal to the original when played at the same time. This is only true of periodic waveforms. So in our plugins we have 3 kinds of delay typically. We have pure delay, we have feed forward delay and feedback delay, and we use these different forms of delay to achieve different things. So an example of pure delay is just the standard digital delay line. So essentially you've got an input signal and you pass it through the digital delay line, and it will shift the signal in time by n samples. So that n can represent any amount of samples depending on the amount of delay that you'd like. The second kind of delay structure we might have is an FIR comb filter. So what this does is essentially split the input signal and then passes one of the signals into a delay line, and then we essentially mix the original signal with the delayed signal together with a gain coefficient G, which will essentially dictate the amplitude of the delayed signal. So this creates delay while also retaining the original signal and blends the two together. And because there's no feedback, the delayed signal is just repeated once with an attenuation determined by the filter coefficient. So this figure shows what happens if you put a impulse into an FIR comb filter, and as you can see, that impulse is repeated with the delay and also an attenuation. So the second structure is an IIR comb filter. So an IIR comb filter is similar to the FIR comb filter, except the digital delay line is actually fed back into the original signal, which produces infinite repeats. However, the repeats are attenuated by the feedback coefficient G. So with a feedback coefficient of 1, the signal will repeat at the same amplitude forever, essentially. With a feedback coefficient of 0.5, it will half every time it is fed back into the delay line. So similar to before, this figure shows what happens when you input an impulse into an IIR comb filter, and as you can see this time the output repeats itself. However, because the feedback coefficient is below 1, it decreases each time, and there's also an exponential decay pattern that you see going on as it progresses. The IR filter attenuates each repeat, but it decays exponentially. So with our audio plugins, we're working with real-time audio. So when we're implementing delay in real time, we need to use a data structure known as a circular buffer. And essentially what a circular buffer is it's like an array which allows you to store the past samples of the signal that has just been entered into the processor, and allows us to index which samples we want in at the current time period. So we typically use like a vector or a pointer array or something like that to store our past values. So I've got a little animation which kind of explains. how the circular buffer works. So here we've got essentially an 8-value array. In reality, your buffer will be hundreds, potentially thousands of samples in length. It's just easier to conceptualize it as an 8-index array. So you get 2 pointers, a write pointer and a read pointer. So in this animation, the write pointer is the red arrow and the read pointer is the blue arrow. And what the write pointer does is input a sample from the current time period into the buffer. So this buffer is separate from the audio buffer. This is separately allocated memory, specifically to store past samples. And so the write pointer will continuously move along as the audio is playing and push that sample into the relevant part of the array. And the read pointer will follow the write pointer with a delay of n samples. So in this case, there's a delay of 3 samples. So the read pointer does not follow until 3 samples have passed. And then after that, it will maintain a gap behind the write pointer of 3 samples. Now, when the write pointer reaches the end of the buffer, it will wrap around back to the first sample and continuously write the buffer over and over. And we use modulo to reset the buffer index. I'll show you that in the code later in the video. So what this does is means that you don't need to store the samples forever. You can just store, say, like half a second of audio. If the maximum delay that you need is half a second, you would store half a second of audio and it would continuously overwrite it. And because you're not accessing more than half a second a delay, the half second sample will still be in the buffer. And so once we've finished the process, we stop the audio plugin. We need to reset the buffer ready for the next lot of audio. So we flush it with 0 samples and the process starts again. So this time we're going to have a delay of 6. And as you can see, the write pointer goes along inputting current sample values into the buffer, and then the read pointer goes through the buffer acquiring the delayed signal. So when we're working with digital audio, we are working in samples, and the computer has next to no understanding of time other than data inputs and the rate of data input. So when we're working with seconds, we need to convert our parameters into samples. So the way we do that is we take the delay time in milliseconds or seconds. So sometimes it's easier to work in milliseconds and then convert it to seconds, and we times that by the sample rate. So that will give us our delay time in samples. So if we want 500 millisecond delay, we divide it by 1000 and get 0.5, and we times that by the sample rate, so 44,100, and then we end up with 22,050, and that will be the amount of samples we require for half a second delay. Now, if the sample rate changed to 48 kilohertz rather than 44.1 kilohertz, our half second of delay would be 24,000 samples. So we do that in code in our plugin so that our delay time scales based on the sample rate of the DAW or the plugin we're working with. So sometimes we would like to link our delay time to the tempo of the project we are working on. And the way we do that, typically our framework will have a way of getting the tempo of the current project from the DAW. JUCE has a method for this, which I will demonstrate later. And so if we take the BPM of the track and divide it by 60, that will give us our quarter note delay time, and you can calculate the rest of the note values from that value. So I've created a plugin to demonstrate how you would implement a delay plugin in JUCE. I would encourage you to download it from the GitHub that I've provided in the description and have a good look through the code. Take your time, get to know it. So looking at the code within the plugin, we've got public member functions of the circular buffer object and the private member variables, and also an additional linear interpolation function. I wouldn't worry too much in this tutorial about it, but essentially what this allows you to do is calculate fractional sample values. So when you calculate the delay time in samples from milliseconds, you often end up with, say, 538.76 samples. So that allows you to interpolate the value between the two samples in which the fractional sample value sits. So if you just do this without interpolation, it will just snap it to the nearest integer, because you need an integer value when reading from the buffer. This mainly reduces clicks when changing the delay time. So if you don't implement interpolation, you might get a little bit of clicking in when you're changing the delay time slider. and it's good for pitch shifting effects and other things like that. I won't go much deeper into that in this video. So you can see at the bottom our data structure that we're going to use for the buffer is a unique pointer array, specifically floats. That's typically what we're working with in audio plugins. This is a smart pointer, so it will self-delete when it goes out of scope, so we don't need to worry too much about memory management. It'll sort itself out. So on the right, we've got the initialization function of the buffer. So it takes an input variables of the sample rate and the max delay time in milliseconds. So what that will do is allocate a buffer length based on the maximum delay time. So it will calculate the maximum delay time in samples from the millisecond input, and that will be the buffer length. So going back to our half second example, if our sample rate is 44.1, our half second of delay would be 22,050, and then that would be the length of the buffer. However, this would mean that we could not have a delay time of greater than 0.5 seconds. If we wanted a delay of 1.2 seconds, we would need to recalculate the buffer length based on that maximum delay time. It also resets the buffer with zeros and initializes the right index to the start of the buffer. So this is in the JUCE plugin itself. So in the prepare to play method, we will initialize our buffer. So we take the sample rate from JUCE, and in this example, the maximum delay time is 2 seconds, so 2000 milliseconds. So in our buffer read function, it takes an input variable of the delay time in milliseconds, and there's a Boolean option to interpolate the delay time. So for this example, I've set it to false, but if you are feeling confident and would like to experiment with that, I left it in there for you to try out. This function essentially, it calculates the read index based on the right index and applies the delay time in samples, and then it will wrap the read index into the buffer using modulo. So essentially, if the read index was higher than the buffer length, it would wrap back round to that delay time within the buffer bounds. So if your buffer was 50 in length and the read index was 52, it would wrap back round to 2. So calculating our delay time sync, we take a BPM as an input. We also take an integer value for sync setting. So I've calculated the quarter note delay, and from that, all of the remaining delay times you might want in a sync setting. This is not an exhaustive list, but this is most of the values you might want to use. And I've just put all those into an array, and that sync setting integer variable from the plugin allows you to choose which sync setting. And this calculates it in seconds, so it's scaled up to milliseconds on the return. This is how we acquire the BPM from the DAW in JUCE specifically. In different frameworks it'll be slightly different, but it's the same principle. So in JUCE you have the audio playhead current position info class, and you just call that. And then in our final delay time calculation, what this is doing is basically saying, is the sync enabled? If it is, you get the playhead.bpm, so that's the BPM of the track, and push it through the calculate delay time. And if not, just take the delay time in milliseconds straight from the plugin. So that means in this plugin, if sync is enabled, the delay time parameter in the plugin is redundant. And finally, our plugin processing. So this is the mono plugin processing method. The plugin that I've created for the purposes of this video is stereo, but for now I'll just go through the mono processing. So essentially it gets the input sample from the JUCE buffer, saves a copy of that to the dry channel, then you get the output of the delay line using the buffer read function from earlier. Then you calculate the buffer input, which is the output times the feedback plus the original sample, and then we are pushing that into the buffer. So that's our feedback. When we push the buffer input into the circular buffer, it's a little bit hard to get your head around, but that buffer read function 2 lines above is where we get the output for the previous buffer writes, and then the output is calculated using a standard mix method. So take a mix percentage from a plugin parameter and then calculate the blend of the dry and the wet signal, and then we push that out to the channel buffer with our attenuation of the standard master level control. So I'll just demonstrate how the plugin sounds with various settings and tempos. thank you for watching. I hope you found this video useful, and if you did enjoy the content, maybe consider subscribing and viewing some of the earlier videos. I had some feedback on the previous videos that some of the content was a little bit too fast paced, there was too much information packed into small sections, so hopefully this video has been paced a little bit better due to the manual voiceover, and I hope to improve at these as I do more. As I said in the start of this video, I'm looking at expanding into more general digital audio education, so if you do have any video suggestions, let me know. I do plan to continue doing the audio DSP stuff though. So thank you for watching, and I'll see you in the next one.